Oh, thank goodness. Can you hear me, Tyler? No, I cannot hear you.
Did you get it figured out?
Good evening, guys. Can you hear me all right?
Yep, you can. We're just having some technical difficulties with Tyler here. We're trying to get it figured out.
Fair enough.
Hey, Tyler, while you're figuring that out, could you give me screen sharing? Perfect, thank you. And we're just waiting on the rest of our team to show up. I expect that they'll be here shortly.
Fair enough. How's your build been going along?
It's been coming along pretty good. We still got a little bit of work to do, but I expect that by the end of next week, we should have it completely done.
Good. Have you guys had any test launches? I thought I saw that you did, but I also saw something that you didn't in your third progress report. I wasn't sure.
We have not had a test launch. That's due to a couple things. First, I was focused on getting my level 3 done, so that way I could be the flyer record for our team. And then the second thing is that there are no more launches in Utah, and even if we did launch, the highest waiver we can get is 10,000 feet. And for our rocket, that's just not going to work.
And they're probably not going to want you to go that tight to the waiver. So sure.
No.
So were you successful in getting your level 3?
I was, yes.
Fantastic. Congratulations.
Thank you. I need to contact, I'm not sure who to contact on that because I need to get me switched over to be the flyer of record. I just got notification just a couple days ago that it's official. So
all you need to do is bring assume you should get your level 3 card in plenty of time. Bring that with you and then you can just show them.
Okay. Yeah, it's just it's a digital copy for student memberships now. They don't send a physical copy anymore, so I assume a picture would probably be fine.
Yeah. So, do you launch rockets other than for the cup, or is that a hobby of yours, or is it just something you did to be part of the team?
This is a hobby that I do. So I've done this for about 6 years now. I've done high powered rocketry for about 6 years.
And who did you cert through? Tripoli or NAR?
Tripoli.
Okay. Can you throw this in the fridge, sweetheart? Thank you.
And where are you based out of, Rob?
Michigan.
Michigan. Okay.
Sorry.
That's all right. one thing with, I see you're recording the session and thank you for that. There is a link on HeroX once you get your recording saved off. If you can send the link to that update in HeroX, that way that gives them the things they need. And if you can copy me on it as well, that way if for some reason it doesn't get to them through the HeroX system, I can send it to them.
Okay, perfect. We can do that. Will you take care of that, Tyler? I think it's recording on your computer. Maybe it's on mine. We still can't hear you, dude.
Her heads up, she's got some good of it. Can't have this lemon juice for what I want to do. You want to do? I need the cup of lemon juice instead of.
Microphone.
There we go.
There we go. Okay. I every time I open up Zoom, it doesn't automatically choose the microphone. I have to go and manually do it.
Okay.
But yeah, I'll get this recorded. I think I have a limit of 45 minutes. I'm not sure if I'll just be able to restart the recording after that and then just merge the two videos together, or if I'll have to start recording another video. But once we get to that point, I'll figure it out.
My suggestion would be if you can, I don't know what kind of presentation you have, but if you can let me ask some questions and things, we can get through things pretty quickly. And then we can do the presentation after the fact if you'd like to. That way you can get to the point where I'm saying, yes, you guys are going to be fine. I'm going to score you as passing and ready to fly before your 45 minutes are burned.
Okay, that sounds good. We can do that.
So does somebody have the rocket?
Yeah, Jorge does. He's on his way. He said he might be a few minutes late. Xavier, Sam, welcome.
Thank you.
I'm gonna guess that you'd like me to wait until you're done with your meeting before I start running like the mixer and everything.
In an ideal world?
That's right.
Okay.
The cake's gonna cool overnight before I exit anyway, so.
While we're waiting, Zach, obviously you've got your L3. Is there anybody else on the team that's high power certified?
Tyler is
At what level?
1.
Okay. Then I guess while we're waiting, you tell me, Zach, is there any part of your rocket you have concerns about? That from a flight safety standpoint, you're not that comfortable with it.
From a flight safety standpoint, as far as the rocket goes, I'm actually very comfortable with where it's at right now. The number one thing that I'd be most concerned about is our air brake system. All the flaps, there are 4 flaps on the rocket, and we'll show you a picture of that later. But there are 4 flaps on the rocket. They should all deploy at the same angle. I'm just worried that something may or may not happen. But other than that, I think we're pretty comfortable.
Is there anything in the air brake system that has the possibility of interfering with flight events?
No.
Chute deployment?
No.
Okay, then from a flight safety standpoint, most air brake systems are kind of inconsequential. I mean, and I understand you're trying to win a contest here and the points are important to you. I get that. But
Exactly.
From my standpoint, just looking at, is this rocket going to be safe to fly? The air brakes are really kind of it's kind of like the payload. Other than making sure it doesn't interfere with flight events, that's really all I'm worried about.
Right. Yeah. Yeah. It shouldn't interfere with flight events at all. There's nothing. Our parachutes are connected to the top of the cage, but we've taken lots of steps to make sure that is secured inside of the rocket. The air brake system actually bolts into the motor, and then the whole system is held in place with 4 bolts, so that way that bolt cannot unscrew on the way down. And then the
bolts go through the airframe?
Yes.
What's your airframe made of?
Fiberglass.
Okay. Are you using washers or anything to secure that, to try and cushion the bolts against the fiberglass?
No, it's just a button head screw.
Okay. Are you at all concerned that shock loading can cause your fiberglass to fail around the bolt?
No, I'm not. There's not the bolts aren't there to take the loading of the parachute. The loading of the parachute will go completely through some all thread rods going through the cage, and then that is transferred to the motor, which is secured with a Aeropack motor retention system in the back.
So the 4 bolts are really just holding the cage in place until the motor's loaded, but it's actually the retainer that's taking all the force.
Exactly.
Okay, fair enough. Good.
Well, Jorge's taken a little bit longer than I expected. Should we just get started with the presentation? I don't want to waste your time.
Yeah, but you keep in mind what I'm looking for is safety issues. You can glance through the payload section and things like that, but that's not what we're really here to discuss.
I understand. Okay, we'll get started then. Okay, well, thank you for coming to USUSpACe Safety Review presentation. Just to kind of introduce the team, my name is Zachary Foster. I'm the team lead. I'm also the flyer of record for this team. Also not here with us right now, Jorge Hernandez Romero. We're waiting on him. He's got the rocket. He'll be here. Xander Summers. Xander was unable to make it. Xavier Tipping, he is on the call. He is in charge of the ACS system, and then he's also done most of the machining on our rocket. And he is also in charge of the GPS recovery. Then we have Tyler Gardner. He's in charge of payload and payload integration. Jonathan Thompson, he's also unable to make it with us. He's a firefighter out in Elko, so he wasn't unable to make it with us. But Jonathan was responsible for most of the CFD work that has gone on in this project, and then Sam Murdoch has done most of the mechatronics work going on in this project with the ACS system. Just going over the airframe. So it is a transition design. So we transitioned from a 6-inch diameter rocket down to a 5-inch diameter rocket. The rocket in total length is 113 inches. The booster diameter is 5 inches in diameter. Payload is 6 inches in diameter, as I mentioned before. The motor diameter is 4 inches or 98 millimeters. Center of gravity is 63.1 inches. Center of pressure is 85 inches, and those are both measured from the nose. Number of fins is 4. it's not listed on this slide, but we'll go over stability later. That gives us about a margin of stability of a minimum of about 2. Vehicle weight, completely unloaded, is 30 pounds. Empty motor case, we're using an Aerotech motor casing. It is 4.6 pounds. The propellant weight is 12 pounds. And then the total liftoff weight sitting on the pad is about 55.6 pounds.
Are those actual measured weights, or is this all from your simulator?
These are measured weights. We were able to measure the airframe.
Okay.
It's mostly put together, so we have a pretty good idea of what it's doing. Airframe material, it's a filament wound fiberglass, so it's G12 fiberglass. And then the fin material is G10 fiberglass. That's just the plate fiberglass, also known as FR4.
COTS or SRAD?
Sorry again.
Your fiberglass, is it COTS or SRAD?
COTS. It's purchased from Wildman Rocketry.
Okay, fair enough.
The structural epoxy used is 3M DP460 and DP420. The differences between those two is cure time. DP460 is a 60-minute cure epoxy, and the DP420 is a 20-minute epoxy. They're both the same formulation. Both of these were picked due to the high shear and peel strength of the epoxy. It is also designed to be used with composite materials, which is why we primarily chose it for this. All the non-structural epoxy that was used is JB Weld 5-minute epoxy. So things for structural, that would be everything that has to do with retaining the motor tube, retaining the fins, gluing the transition into the payload section, anything that's going to be taking any kind of load during flight and during descent.
So what did you use the JB Weld on?
We use the JB Weld on to glue bulkheads together. So we use a thinner fiberglass material, and then we just doubled them up and we glued those together. We also use JB Weld in our payload system to glue that together. And then we also use JB Weld to glue in our GPS tracking system, which goes into the nose cone. Moving on.
May I ask
Yeah.
why you chose JB Weld?
It was cheap and we could get it at Home Depot.
Okay.
We felt like we weren't using it on anything that was flight critical, and we used the better epoxy for things that were flight critical.
Okay, and why did you make that decision to use the JB Weld but in non-structural settings? What drove that decision?
Because we wanted, so first of all, flight safety was the first thing. So we wanted to use proven epoxy. I've had lots of experience using this epoxy. We've used it on other projects and it has worked quite well.
You're talking the 3M epoxy there.
Yes.
Okay.
So the 3M epoxy we've used on surface mount fins. I did a 2-stage project a while back, and we just surface mounted these fins, and there was no fiberglass layup or anything on there, and the fins held up great, which is why I was inclined to use that kind of this epoxy for that application. The JB Weld, we used that just simply because we had it on hand. There wasn't a huge design thought into using JB Weld. It was just something we could go down to the hardware store and get. We didn't have to special order it.
And are you talking an actual 2-part epoxy with JB Weld, or are you
Yes.
talking those 2-piece putties that they sell as well?
It's a 2-part epoxy.
Okay, fair enough.
2-part epoxy. All right, moving on to our fins. So we'll show a picture of the fins later. Jorge, well, we can show them now. Jorge got onto the call. So our fins are through the wall mounted. So we were able to machine slots into our fiberglass tube, so that way on a 3-axis mill to ensure that all the fins are aligned properly. The root cord of the fin is 12 inches long, tip cord is 5 inches long, and then the semi-span of the fin is 5 inches long, and then the total tang inside of the airframe is 5.7 inches long, and the tang goes the whole width of the fin, and then the tang of the fin is actually sandwiched in between 2 bulkheads to ensure that they don't move. Internal fillets were done by drilling holes into the airframe and then ejecting the epoxy in using a syringe type of tool, and then the holes were later filled with the same epoxy. All of our fiberglass components were sanded they were first wiped down using soap and water, and then later with acetone right before we were applying our epoxy. Then they were sanded to 220 grit, and then they were cleaned again with acetone before the epoxy was applied to all of our fiberglass components. Then we added chamfers onto the leading and trailing edges. This was to reduce the vortex shedding off the leading edge, which causes fin flutter, and we'll go over fin flutter on the next slide. In hopes that we can avoid fin flutter at all costs, we're pretty far away from our flutter speed, and we'll talk about that in a second.
You guys are 10K? You're flying in the 10K category?
Yes, sir.
And what motor are you using?
It's an M2400.
Okay, fair enough. Yeah, you're not going to get into transonic speeds.
No. Jorge, if you could show the fin assembly, that'd be great. And then those are 1/4-inch fillets on the outside
Made of?
of the same 3M epoxy that we spoke of previously.
Put any thickener in it or anything, or just use straight epoxy?
So there's two formulations. There is the non-sag formulation, and then there's the regular formulation. They're the same thing. There's just one thicker. The internal stuff was the non-sag formulation, so the less viscous mixture, and then the outers were done with the non-sag, which has a higher viscosity.
Okay.
So we didn't add any filler, but the manufacturer did.
Very nice. That looks good. Can I see the retainer, please?
The back end where the motor goes in, Jorge. Our retainer is an Aeropack retainer. That's a bolt-in retainer.
Have you tried to actually fit your motor case in yet?
So we have a loaner casing that we can use. We haven't picked it up yet. And we do have propellant in hand. We're just using a loaner casing because unfortunately it did not arrive in time.
Okay.
But
Did you by any chance use an Aeropack retainer on your level 3 rocket?
I did.
Okay. Did you have any trouble fitting the motor?
No, sir.
Okay. I have found, having used a lot of Aeropack motors, that when you tighten those bolts down, it tends to shift the retainer a little bit out of line.
Okay.
So make sure you bring along to the competition whatever Allen wrench you're going to need to loosen those a half turn if you need to, so that when you get to your competition and you try and slide your motor in, if it jams, you can back those off, put your motor in, and then tighten them down again.
Okay, so the bolts actually are not removable. The Aeropack retainer actually has a twist knob. If you could untwist it, Jorge, and show him the retainer. Untwist the retainer and show him the back end. Could you take the cap off, Jorge? There's a twist cap on the outside, and then the retainer is bolted onto the back.
Right, and I'm talking about the bolts that hold the retainer onto the airframe itself.
I understand. Okay, I understand.
Those sometimes, when you tighten them down, it throws everything a little bit out of alignment, and so you need to loosen them in order to get your motor in.
Okay, I understand. Sorry, I just misunderstood. Okay.
Yeah, I'm with you.
Okay, thank you.
Okay.
So our fin flutter analysis, we just use the fin flutter boundary equation. I do recognize that there are other methods of calculating fin flutter boundary that probably give us a little bit higher fidelity. But just from
if you were pushing the boundaries or something, you might want to have done a second analysis. But since you are so well under any level of concern, I don't think you're 38% of your flutter speed. I think you're fine with this.
Yeah, yep, that's the same conclusion we came to as well. So we are using a commercial off-the-shelf motor manufactured by Aerotech. The specs are shown below. It's an M2400. It is a 98 millimeter motor. We do have our motor propellant We are using a loaner casing, and hopefully our actual casing arrives in time, but we do have a backup in case that doesn't happen. Going on to our flight simulation. So we used OpenRocket as well, but all of our flight data came from RAS Aero. I used RAS Aero on my level 3, and I was able to corroborate the data that came back from RAS Aero, and we got within 5% of what the simulated flight was going to be. So I have a high level of trust with RAS Aero, but as before, they are just simulations. So this is a nominal case. So our apogee is expected to be about 11,000 feet. Maximum velocity is 991 feet per second. Maximum acceleration is about 10 Gs. Minimum stability, and the stability graph is shown in the bottom left, or bottom right, excuse me. And our minimum stability is 2.15, and then after motor burnout, it's just shy of 3. And then our thrust to weight ratio is 9.87, and our rail velocity is 103.3 feet per second.
Very good.
Moving on to recovery. So we are using, for our drogue, a Rocketman 4-foot parachute. It's got a drag coefficient of 9.7. The drogue descent rate is about 60 feet per second. All of our quick links are going to be 3/8. We don't have the recovery harness installed into the rocket yet. It is in my storage unit. But all of our quick links are going to be 3/8. We are going to be using a swivel going from the shock cord to the parachute, as per the requirements from the DTAG. Our primary flight computer is a MissileWorks RRC2 Plus. I've used this flight computer many times. It's my primary flight computer on all of my flights. It's very easy plug and play, very simple to wire. The main parachute is also a Rocketman parachute. It's a 14-foot parachute in diameter. It's also got a drag coefficient of 9.7. The main descent rate is 14.5 feet per second. And our shock cord is rated to 2,000 pounds, made of Kevlar. Kevlar was chosen because it has a high strength, and it also can handle the ejection charges. And so we don't have to have, for example, with nylon, you won't have to worry about the shock cord melting due to the ejection charges. Our secondary flight computer is also MissileWorks RRC2 Plus. And our wiring diagram is shown below. Both systems are electronically isolated from each other, so they're fully independent of each other. We are using a lab rat rocketry full pin switch. I've used this on several projects and had good success with it. The nice thing about the RRC2 Plus is because we are using 2 of them at the same time, you can actually change the tone of each one to a high beep or a low beep, and then you can distinguish which one is on and which one is off. And that makes it easier for boot up processes while you're out on the pad, and then also for continuity checks on your deployment charges.
Does somebody have your electronics, your sled, that I can see it?
We do not. It is 3D printed. I can send you a picture of it. It's a 3D printed sled. It's mounted on 1/4 inch all thread rod, and then it's bolted in place with 1/4 inch nuts.
Okay. How many threaded rods?
2.
Okay. And on your wiring diagram, you've got a designation JSTW to W. Not sure what that means.
So is the JST connector. It's commonly used in aircraft components for model airplanes. I also do model airplanes as a hobby, and so those commonly experience high amounts of Gs, especially during flight maneuvers. And W to W means a wire to wire. There's several different types of JST connectors. You could have a wire to a board JST connector, for an example, or other types of JST connectors. But JST connector is just it's the standard. It's just the name that they call it in the electronics world.
Are those mounted on your end caps to your electronics bay? Or
No,
are they free floating, or are they on the exterior of your electronics bay?
they are free floating. They're on the inside.
So this is connecting your wiring from your altimeters to your deployment charge wires.
Yes.
So your deployment charge wires, your pigtails are going to be passing through your bulkheads.
Yes, and then on the outside, they'll be connected to Wago nuts, so Wago lever nuts, and then the hole that they pass through is going to be epoxied closed. That way, no
And what's the
deployment.
purpose of the Wago then?
So that way we can easily attach our deployment charges onto the Wago nut, and you don't have to use any tools to attach them. It's just a lever.
So it's not actually the E-match that's connecting to your JST.
No,
It's your JST is there's another wire running from your JST connector up to exterior of your avionics bay, and then you're going to use Wagos to connect from those wires to your actual E-match.
correct. So the JST connector just allows us to take the bulkheads off so we can assemble it.
Gotcha. Okay. And so how are you passing your wires through the bulkhead and making sure it's an airtight connection?
We are going to be just drilling a hole through it, passing the wires through, and then we're going to epoxy the hole closed, and then put that JV weld putty that you previously mentioned on both sides to make sure that it's an airtight seal.
Okay, because these are wires that you are not anticipating having to remove again. They're not part of
Yes.
the actual E-match.
Yes.
Okay. What are you using for batteries?
9-volt batteries, lithium ion.
What kind?
Just the regular Duracell.
Okay, but you are specifying Duracell?
Duracell, yes.
Okay. Do you know why I'm asking?
Why?
No, I'm asking if you're aware of why
Oh, I
Duracells
am
are
not.
more important. Okay.
I'm not.
9-volt batteries tend to just be press fit together. So the internal components are just shoved up next to each other, and it's the pressure of the case itself that holds everything together. Duracells actually are internally tack welded. And so under the high G loading and the vibrations of flight, they tend to have a higher ability to resist losing power halfway through the flight. Whereas Evereadys and certainly any of the off brands or rechargeables have a habit of turning themselves off because they lose contact halfway through flight.
Oh, okay. Okay. Well, that's good to know. We will definitely 100% make sure that they're Duracell then.
Excellent.
Just so I can interject real quick, we have 7 minutes on this meeting, and then I think the meeting will kick us out, but I'll start up a new one, and I
Okay,
can
will
send
you-
the link
Yeah,
back
will you
in.
make a new link? That'd be great. Thank you. And send it in the chat and we can all save it. Perfect. Thank you. Okay, I'm going to hand you off to Sam, who's going to talk about our altitude control system.
Perfect. So this is our altitude control system on that diagram for the right. Like Zach mentioned a little bit earlier, these flaps will extend out. There will be 4 in total, 1 from each side. They're positioned that way the slipstream will not have any interference with the fins on the bottom. Once those flaps extend out, it'll increase drag, it'll do its thing. If you look at this diagram, the top half consists of the motor and the batteries. Above the motor and the batteries will be the electronics bay. That'll house all the smarts to actually make this work. That'll control the stepper motor, which will turn the power screw in the middle, raising that central nut up and down, which controls the flaps. Because of how it's designed from a safety perspective, this should make sure that if we lose power, if something unexpected happens, this won't really move or change in any way, since the stepper motor connected to the power screw shouldn't be able to move if it's not under power. The flaps are also designed in such a way that it really shouldn't be able to move one side more than the other unless something breaks, which, Zach, if you will move to the next slide, I believe that has the factors of safety. These are the factors of safety that we calculated based on mechanical methods. We calculated most of these with some pretty extreme parameters. When we were first designing this, we wanted to make absolutely sure nothing would break. So our lowest factor of safety right now is 1.2, but I'd like to point out that that's in case we have about 1,500 pounds of weight and force on the parachutes, which really isn't going to happen in any circumstance. This really shouldn't be breaking or having any kind of mechanical failure, so there's no reason to think that we would have that scenario where one of the flaps is at a weird angle and it's making the rocket do some altitude and attitude weirdness. Next slide, please, Zach. This is our electronics wiring diagram. It looks awful busy, but that's because what we're using is called the featherweight line of Adafruits. Basically, they just snap on top of each other. Real simple, really hard to mess up. We'll have that connected to a motor controller, which is a little bit beefier and a different brand, which is then connected to 3 LiPo batteries connected in series to power the stepper motor. Again, this looks pretty busy, but it's pretty straightforward in practice. Next slide, please, Zach. Finally, we have the software control loop. This is pretty simplistic. To be honest, everything from the electronics to the software is still a little bit of a work in progress. We have everything penciled out. It's just getting it all to work together. It's still on the table, but the software, as you can see, will get the sensor data, filter that out into something useful, format that into something we can use, and then we will check our current trajectory against what would happen if we extended the flaps to a certain amount. We will compare which one would be best for what we want to get to our goal trajectory, and we'll take that course of action. We'll have the motor do its thing, and then we'll take the new sensor data and just keep looping that through, so that way we will asymptotically approach our goal as we get closer to it. That's it for the overview of this. Do you have any questions on the ACS I can answer for you?
Yeah, go back to the first slide. There you go. The drogue parachute attachment, that's the top of the rocket.
That is
Towards the pointy end.
Yes.
Okay.
That's correct.
So the flaps are opening up into the airstream instead of dropping down into the airstream.
Correct.
Good. Does your ConOps have the flaps retracting after they've been used?
We did not have that initially, but I could easily include that.
Yeah. Oh, sorry. I didn't mean to interject. We were planning to retract the flaps before the parachute deployment. So when we get up into apogee, that was one of the things we were planning for, so that way it doesn't get in the way with the parachute cords.
The one I was concerned about cord entanglement. The other thing is one of the criteria that your rocket is going to be judged on in the actual contest judging for score is reflyability. Can your rocket be reused as is without repair? And if you landed that rocket on that hard desert playa with those flaps extended, the chances of them jamming or breaking are going to affect your reusability score. So you will definitely want to be able to retract. You want to retract them if you possibly can. Go over to your software page. There you go. Now, you said that this was still a work in progress. If it doesn't work out the way you want it to, do you have the capability of having the air brake system simply fly along during the contest and not deploy?
Yes, we do.
Okay, great. And that's not going to affect any other flight parameters or anything?
No, it's an independent system, so this will be just fine if it just stays neutral.
Or are you powering it?
With 4 LiPo batteries.
Okay. Have you heat tested those LiPos yet?
I haven't tested these specific LiPos, but they're 2 to 3 times larger and more durable than I was planning.
But
like for our worst case
my
scenario?
concern is not power or voltage. It's what happens when they sit out in that field for an hour and a half because the rocket before you KO'd and there's a fire that has to be put out. And now the sun has been beating down on them, and the interior of that motor mount, that airframe is now 180 Fahrenheit. What are those LiPos going to do after being soaked in that much heat for that long?
I've not tested that case, but we can test that before launch.
Just something to consider. Now, I'll be honest, your air brakes aren't flight determinant. I'm just trying to think about some ways that you can make sure your rocket flies more successfully.
Okay, we are about to get kicked off. So Tyler is going to have a link ready for us as soon as we're done. We've got less than a minute, so I expect any second now we're going to get kicked off.
Or we can just go ahead and jump off now and then start back up under the new link.
Okay, let's do that. Okay, thank you. Okay, there we go. All right. Is there any more questions on the air brake system?
Nope.
Okay, I will turn you over to Xavier for our GPS tracking.
So it's pretty simple. We're using the Big Red Bee GPS. We're putting it in the nose cone. The nose cone's currently black. I guess if you want, Jorge, you can show the nose cone. Do you have the bay where it fits into? Like, can you take the nose cone off?
That's not carbon fiber though, is it?
No, the nose cone's fiberglass.
Okay, good, good.
Correct.
And so there's a 3D printed housing inside the nose cone that it fits into. And it'll be bolted in and secured that way. The antenna will stick out, and it has plenty of room because the nose cone's giant.
Sure.
And we'll paint it white just to make sure that it doesn't overheat, because that was something that Big Red Bee specifies in their specs, is since they use a LiPo battery, that you have to make sure that it doesn't overheat.
Yep.
And then we'll have our own ground station using a software defined radio and software TNC. So
Who on your team is ham certified?
I am.
Okay, and you'll be coming?
Yes.
Excellent.
Another note, we also tested the system on my level 3, including the same mounting technique, and that worked perfectly. So other
Great.
than the fact that our software radio died, but we got data, so that was good.
Mhm.
Alrighty, that's all I have for our presentation. Is there any part of the rocket that you would like to see?
Yep, I want to see the rail buttons.
So the rail buttons have not been installed yet. I know that there was a incident with Rice University, or I can't remember which university it was, with their test launch, and rail buttons are a pretty hot topic right now. Once those get installed, I can send you a picture of what they are going to look like. Right now, what our plan is to use a nylon spacer purchased from McMaster-Carr in order to make up the difference between our payload section and our booster section. They'll be about a ½ inch tall, and then they will be secured using a screw that goes all the way through. The aft rail button will be secured using that DP460 epoxy that we spoke of earlier. And then the forward rail button will be secured with a washer with a lock washer with some Loctite on it, and to ensure that it doesn't come off.
Is your forward button on the booster or on the larger diameter sustainer?
It is on the booster.
Okay. When you say you're using spacers from McMaster-Carr, are these cylindrical spacers?
Correct.
So it's really the longer bolt that's running through both the button and the spacer that's giving you structural strength?
Correct. There will also be a bit of epoxy run, at least on, well, yeah, for both of them, there'll be a bead of epoxy running around the spacer onto the airframe to provide some structure that way. The forward rail button needs to be secured with a washer, so we can take that screw out, so we can get all of our guts inside of the rocket. So our air brakes need to slide in through that way.
Have you considered any sort of conformal lug to use as a spacer instead of the tube, the nylon spacer?
Conformal by just conforming, like, explain that to me, sorry.
Think about how a shroud, if you were to mount a camera on the outside of your rocket and it had a shroud on the outside of it, using something that basically looked like that, but was obviously not at an angle, to create a structural connection between the base of your rail button and the airframe itself.
Okay,
I'm concerned that the weight of your rocket, especially under the forces it's going to take during launch, sliding up a 17-foot long rail, that you're going to overwhelm that nylon spacer is really not structural. It's just a spacing. It's a washer. That's really all it is a tall washer. And you might want to consider a more structurally solid way of mounting your rail buttons, standing proud of the side of your airframe.
Okay, And so what would be a method you would suggest? So the conformal, so what? Yeah, I'm just trying to think of a way that we could do that.
Literally taking a wood block or 3D printing a mount that has the same shape as the outside of your airfoil, and then it is epoxied into place, or it is bolted into place, maybe with a front and back bolt, and then your rail button is through bolted through that mount and into the side of your rocket, or only through bolted into that mounting unit, so that you can still get your internals in and out of your rocket easily, because now it's being mounted externally instead of being mounted through the wall. A couple of different ways to approach it.
Okay, I understand. Yeah, that's something that we can easily do. We have a 3D printer on hand. We can easily do that.
Keeping in mind, of course, 3D printers are the PET and PLA are crappy materials to try and epoxy. You're going to need to try and figure out some sort of scheme to get those things to really adhere to your airframe.
Yep. Both of those are easy. We can figure a way out.
Okay. Let me see your connectors.
Okay, so that'd be the coupler, Jorge.
Couplers. Thank you. The word fell out of my head. Thanks, Zach.
You're all good. You're all good. So there's only one coupler, and it's got a 5-inch diameter coupler.
Wait, the one on the nose or the one down here?
It's the electronics bay. It should be attached to the payload section. Well, there's one coupler. So the coupler on the nose cone. Yeah, there you go. So
And
that
is that coupler permanently bonded to the forward airframe?
Correct.
Okay.
And then it sticks out 6 inches into the 5-inch diameter airframe.
So are you using shear pins to keep your pieces solid and flight until your ejection charges go off?
Correct.
And what kind of shear pins are you using?
Nylon number 2s.
How many?
4.
Okay. And you've already, that tube looks awfully clean. I'm guessing you have not ground tested yet.
Not yet, no.
Okay, you're going to ground test to make sure your deployment charges are properly sized?
Yes, sir.
Okay.
We can send you videos once that happens.
Okay. And I'm not necessarily worried about that, as long as you know it's a good deployment charge. That's really what we were concerned about. Just make sure you bring your results so that your on-site flight safety person sees it.
Yes, sir.
And then you're also using 4 number 2 bolts at your joint with your nose cone?
Correct.
Now, looking at the that joiner, that coupler that Jorge is currently holding, that looks dramatically smaller than the thickness of your body tube. Or is your body tube actually a 1/2 inch thick?
So it's a transition design. So it goes from a 6-inch diameter airframe. So that's what the piece that Jorge is currently holding goes down to a 5-inch diameter airframe. And then there is a 3D printed transition.
Gotcha. Okay. And so once you slide those together, where are the shear pins going to be mounted?
Just aft of the transition. There's enough space there.
They're in the fiberglass to fiberglass joint.
Correct.
Good. I just didn't want you to tear out your transition.
Yeah.
Now, same scheme for your nose cone attachment, 4 number 2, 256 nylon screws?
Yes, sir.
Okay. And how long are your shock cords?
15 feet each.
Are you worried that having your shock cords that short at your apogee deployment, that the forces when your shock cord snaps taut are going to throw your nose cone off and shear your shear pins?
That can happen. We have extra on hand. We can make that 45 feet long. I realize 15, now that you mentioned that, 15 feet is quite short for for that airframe. We can make them, we can triple that.
Okay. Do you know how to daisy chain a shock cord?
Yes, sir.
Okay. I would also suggest you might wait, especially if you don't want to go the full 45 because you don't have enough room inside your airframe or anything, then at least daisy chain your shock cords so that it provides some deceleration as it's expanding.
And just so we're on the same page, you mean daisy chain as in like each loop is taped with tape, right?
No, daisy chain is in a form of knotting.
Oh, okay. Yep, I can do that too.
A slip knot that will basically untie itself, but because you've kept it at least slightly snug, it provides some resistance as the slip knots pull apart in order to try and decelerate the nose cone as the shock cord extends.
Okay, yes, sir. I know how to do that as well.
Okay, great. Are you going to paint it before you bring it?
Yes, sir. It's going to be white.
Okay, good. Do you guys have any questions for me?
No, I just had a question about the flyer of record, but I think we cleared that up at the very beginning.
Then guys, I'm satisfied. I think you've got good experience. I would strongly recommend that as you take this through the flight safety process, once you're down in New Mexico, the first thing you're going to mention is I am level 3 certified. We have other high power certified members of the team, because that's going to let them assume a lot of things they would have to ask otherwise. Keep in mind, a number of these teams that these guys are going to be flight safety checking, this may well be the first rocket they ever fly. Not necessarily the first high power, but the very first rocket. No Estes, no mid powers, no nothing. And so with a team like that, you can't assume anything.
Yes,
But
sir.
with you being level 3 certified, they can make some assumptions and just double check some things, since you obviously know what you're doing and have some experience in doing it previously, which is a huge, from a safety standpoint, a huge weight off everybody's shoulders. So congratulations. I'm glad that things have gone together so well. And I'm sorry you weren't able to test fly, but we've also had some teams that have had some unfortunate circumstances occur during their test flights. And so all of a sudden they are rebuilding the rocket from scratch with only 4 weeks left before the launch. So at this late date, test flying would certainly not be recommended. Unless you have any questions for me, I'm satisfied. I'm going to report your scores in just a moment to Ezra. Please make sure I get the links to the recordings so I can turn those in as well. And guys, I wish you all the luck in the world with the contest, and I look forward to seeing you again in New Mexico.
Perfect. Thank you so much, Rob. We really appreciate all of your help.
You're welcome. You guys have a great evening.
You too.
Thank you, sir.
Bye-bye.
USUSpACe, could you guys hang on for a minute?
All right.
Perfect. Thank you, Rob.
Yep.
Thank you.
All righty, guys. Good job. That went a lot better than I thought it